So you have a circle and you select a random chord. Now inscribe an equilateral triangle into the circle. The question is pretty straightforward. What is the chance that the chord's length is longer than the side length of the triangle? It's a pretty easy question if you ask me. A chord is defined by its two endpoints, and you can rotate the triangle so one of its vertices is one of the chord's endpoints. The chord is longer than the side length if the other endpoint is on this arc on the opposite side. Since that arc's angle is 120 degrees, there's a 1/3 chance of picking the other endpoint on that arc. Wait, no. Each chord is also uniquely defined by its perpendicular bisector radius and its point of intersection with that chord. So we can rotate the triangle so the radius is perpendicular to a side. The Pythagorean theorem says that this length is half the circle's radius. The chord will be longer than the triangle's side if it is on that length, making the probability of a chord being longer than the side 1/2. No, you're thinking about this wrong. Clearly, each chord is uniquely defined by its midpoint, and the region of midpoints whose respective chord is longer than the triangle side is this triangle's incircle. We know that the radius of the small circle is half the large circle's radius, so its area is 1/4 the large circle's. Obviously, this means the probability is 1 in 4. That doesn't make sense. Only one of our answers can be correct. My name is Everyone, settle down. Why are you even here?
We just wanted to watch the video.
Well, are you subscribed?
Yes.
Well, then I guess you can stay. Just don't get in my way. Anyway, we have 3 different answers to the problem, but none of them appear to be logically invalid. Therefore, we can officially conclude that 1/2 equals 1/3 equals 1/4. Just kidding. Obviously, this isn't true, or else all the methods we know would have no meaning, so the very argument to make this claim is incoherent. If 2 of them are false, but only 1 can be right, what is the answer? Think about what you think the right answer is among these 3. As you might have suspected, either because you've heard this problem before, or you saw the contradiction, the answer isn't clearly defined. Something told you that it doesn't make sense for there to even be a correct answer, and that result is called Bertrand's paradox. It was invented by a mathematician named Joseph Bertrand to show that probabilities with an infinite domain of possibilities are surprisingly tricky. The classical solution to this problem is that, well, there is no solution. There is no way to actually solve the problem, and it's a consequence of how the problem is stated. I said word for word, so you have a circle and you select a random chord. How do you select a random chord? This is the primary reason that there are 3 unique solutions, all with different answers. Each one uses a different method of selecting a so-called random chord. You may have been tripped up and misled by the word defined in each of the arguments. A chord is defined by its endpoints. A chord is defined by its perpendicular bisector and intersection. A chord is defined by its midpoint. All of these are true, and if you're given one of these, you can uniquely match it to a chord. So you may think that this makes the distribution of chords uniform, but this is only true when the point distribution itself is uniform. And as you may have guessed by now, the point distributions here are not entirely random. At least, not uniformly random. The perpendicular bisector method weights the points more heavily toward the center, and the reason for this is that when you rotate the radius, you get rings which are smaller towards the center. Points near the center are more likely to be chosen because of this uneven distribution. It's tricky to concretely describe this since you have to be really careful with infinities. After all, that's what Bertrand's paradox is all about. Whenever you say to pick something out of an infinite pool, you must be very careful about how you describe it. There. Now is your conflict resolved? Maybe.
Yes.
So yeah, that's Bertrand's paradox. Thank you for watching, and take care.